So in this second part, let's keep the standard form and the formula on the left side here on the board, and let's continue with another example. So suppose the equation is ty prime plus y equals 1 over t. And by the way, if you get a hang of how you do this, you can actually pause and see if you can actually solve it, and then you look at the answer before you actually see the solution given on the board. Right, so ty prime plus y equals 1 over t. And I'm gonna already, like I said, you can write the solution in advance just to check yourself if you understood the whole process. So here's another one. Let's actually make this an initial value problem. So y prime plus 2ty equals t. Y of 0 equals 5 over 2. And the last one that I want to talk about and give some important remarks on how you actually do it, how you do it efficiently. So that's number 3. The last example 4, let's put one ODE with constant coefficient. So let's say y double prime, let's say plus 3y prime equals 12. Plus 3y equals 12, sorry. So y prime plus 3y equals 12. Okay, so the first thing I want to point out, and again, pay attention here closely. Number 2, this example is not in the proper form. It's not in the standard form. Don't rush and say a of t is 1 and b of t is 1 over t. It's not written in the standard form for which the formula was developed, because you have t times y prime. All right, so you must get y prime by itself. So that means you need to divide the entire equation by t, right, in order to make y prime by itself on the left side. So that means this becomes y prime plus 1 over t times y equals 1 over t squared. So now it's in the standard form, which means you can actually write down now y a of t is 1 over t, b of t, of course, is 1 over t squared. So let's compute the two integrals. I1 is the integral of 1 over t, which is the natural log of t. And be careful when you have natural logs, because you must simplify them correctly. We'll get to that in a minute. And the second integral, I2, is the integral of 1 over t squared, which is b of t. We follow this part here, times e to the I1, which is e to the ln of t. Okay, so we must simplify this, otherwise we cannot compute the second integral. Remember the formula e to the ln of something, you can cross out and eliminate e with the ln, right? So that means this is 1 over t squared times t dt, and that means I2 simplifies to 1 over t dt. So I2 becomes another ln of t. Again, pause for a moment and make sure you understand these algebra steps, because lots of common mistakes happen here when you have natural logs, when you don't simplify them correctly. So let's write down the final solution, the formula for the solution. Y equals e to the minus I1, so that's minus ln of t, c plus I2, which is another ln of t. C plus ln of t. You can leave it like that, but especially if you need to do something else with this solution, you want to simplify it further. Just again, be very careful with your algebra. You can't cross e with the ln like that. You got to bring the exponent of the natural log inside the natural log. So that means y equals e to the ln of t to the negative 1, c plus ln of t, and only then you can cross out e with the ln. So that's 1 over t c plus ln of t. You can leave it like that, or you can distribute 1 over t, and this becomes c over t plus ln of t over t. So don't forget to apply correctly that formula, that algebra formula, right? So which is n times ln of x is ln of x to the n. right? We have to use this to bring in whatever the coefficient natural log has inside the natural log before you can simplify with an exponential. So the second example, let's proceed just like before. So I1, this is again in the standard form. I1 is the integral of 2t dt, which is t squared. And then the second integral, I2, is the integral of b of t, which is t e to the t squared. And notice now that you need to use some technique of integrations, right? In this case, you need to use u substitution. So u equals t squared, du is 2t dt. So this becomes the integral of e to the u. T dt is 1 over 2 du. So it's 1 over 2 e to the u, which is 1 over 2 e to the t squared. So that's the second integral. And then finally the solution to the problem, e to the minus I1 c plus I2, c plus 1/2 e to the t squared. And again, now you can distribute the exponential if you want. And notice if I multiply this with this, is just 1. So actually it looks much nicer if you distribute the e to the minus t squared. I should point out again that in this case, you may recognize why 1 over 2 is a particular solution. Because if you plug in 1 over 2 here, it's easy to see that fits the full equation. So in this case, the particular solution would be easy to guess, but not the homogeneous part. So remember, this formula takes care of both, right? This is the single ODE in which the homogeneous part and the particular solution are solved in the same process. So the formula provides both. As you will move on with other more complicated differential equations, you will need to have two separate techniques, one for the homogeneous part, one for the particular solution. Now the last important example, the last important remark I want to make related to this example, it's very important in this class to use always the easy method whenever applicable. So this equation fits our general formula, but it will be much faster to solve it via the two-step method we know already. So instead of writing this formula, we could just use the two-step method, because the homogeneous part of the equation, it's a simple one. It's the one that you should memorize. That's the exponential ODE. So that takes just a second to solve. YH is c to the minus 3t. And the particular solution is also in the form of a constant. So remember, if you have constant coefficients, it's likely that the solution, the ODE admits a constant solution. What is that constant solution? Well, plug in a constant for y. That constant derivative will be 0. So that means the constant that fits the entire ODE is 4. So the particular solution is 4. And therefore the full solution of the ODE is the homogeneous part plus the particular solution 4. So with enough practice, which you have to do, remember, I mean, I hope by this point things are obvious, right? Practice makes perfect. And it's unavoidable. Without practice, nothing can be achieved in math. But with enough practice, you could actually solve this mentally. It's very important to actually practice with this, because if you cannot solve it mentally, that means maybe that you still have some misunderstandings on the whole process. So how can I do it quickly? Well, let's actually do another example with constant coefficients to see how we can do it mentally quickly. So let's say y prime plus 2y equals 6. What is the homogeneous part of the equation? I drop 6 in my mind, so I have y prime plus 2y equals 0, y prime equals minus 2y, move it over. So the homogeneous part would be c to the minus 2t. You could visualize, if you drop 6, that this is y prime equals minus 2y, that's the homogeneous part of the equation. What's the particular solution? Well, if it's a constant, y prime will be 0, and you're left with 2y equals 6. What is y equal to? That's 3. I can solve it in my mind, so the particular solution is 3. So Of course, this trick again works only if you have constant coefficients. In all the other cases, you need to go through the process. That's why we learned this formula. But if you have constant coefficients, you should do it faster by the two-step method. Otherwise, the I1 and I2 formula works just as fine. So for example, if you want to do it via that formula we just learned today, well, you take I1, the integral of 2 dt, which is 2t. You can take I2, the integral of b of t, which is 6, times e to the I1, which is e to the 2t. The antiderivative of this would be 6e to the 2t over 2. That's 3e to the 2t. So the full solution, according to the formula, is e to the minus I1, e to the minus 2t, quantity c plus I2. And if I distribute e to the minus 2t, I get, as expected, c to the minus 2t plus 3. No surprise there, right? I mean, same solution, but obviously, like I said, the two-step method would have been faster here rather than the more general formula. So with that, that's it for today's lecture. The next and the last one on chapter 2, it's a real-life application for first-order ODE, and that's going to be the next topic.